All right, so let's move away from the optimization stuff. Let's go into something called curve sketching. So we're gonna graph a curve, and we're gonna do it very precisely. So far, for higher degree functions, we've just been kind of winging it. By that I mean when we graph x cubed or something, we know it starts here, we know it ends here. We may know these things, but we don't know where these points end, like something like this. We don't know how far up this goes. We don't know how far up this goes. Yeah? So here today, what we're gonna do is be more precise, but to get there, let's start off with some basic things. So these are the skills you're gonna need to do this chapter. So we have a linear inequality here. How do we solve this for x? So you'd subtract 9. So this will be -7. And then you divide by 3. So that one's very, very simple. So it's going to be -7 divided by 3. What about this one? Not as easy. I can't hear what you're saying, unfortunately. I know you said something, but I can't hear you. I don't know what's going on. So anyways, we're trying to solve this inequality. It's a quadratic inequality, so it's not as easy as the previous linear one. So here what we're going to do is that t squared minus 2t is less than 3. For a polynomial equation, inequality is essentially an equation. You want to move everything to the same side. For degree 2 or above, you have to move everything to the same side. So here what we do is this. You move the -3 to the other side, okay? So now let's factor this. We're looking for two numbers. When you multiply them, you get -3. When you add them, you get -2. What are the numbers? It'll be what? One of them is -3. What's the other one? It's +1, like that. So here this becomes t minus 3, t plus 1 less than 0. So we can graph this function. We know the two x-intercepts, right? Where are the two x-intercepts? So two x-intercepts are at 3 and at -1. So there they are. So we want to see where this function, or this t squared, this quadratic function, is less than 0. In other words, we want to see where it's negative. So there is one here. That's our first x-intercept. There's one here. We don't care about the vertex. We don't care about the y-intercept. I can use a different color. So this one's going to be opening up. Actually, we do know the y-intercept. It's -3, but we don't need it. So this is what we have. These are the two x-intercepts. So when is this function negative? Yeah, I can't hear you quite clearly, but the answer is that it's between -1 and 3, okay? Negative just means below the x-axis, below x-axis. So the answer here is going to be between -1, not inclusive, because if x were to be exactly -1, the y value will be 0. which is not a negative number. We need the numbers to be strictly negative, not 0. So between -1 and 3, the function is strictly negative. Now you can use the interval notation as well, because -1 and -3 are not inclusive. We do rounded brackets. So this is the interval notation. This is like the set notation. And that's the answer to this quadratic inequality. This one, how do we solve this? Any ideas? So just treat it like a linear, like an equals to sign, right? It's an inequality, we know that, but we're just gonna treat it as an equals to sign. If it was an equals to sign, we have linear functions on both ends. We know we have to combine the like terms. For linear functions, you don't have to have everything on the same side. So let's open the bracket. 5 times 3, 15. 5 times -x, -5x is greater than equals to 3x minus 1, like that. Next, group the like terms. I'm going to put the letters, the x's together. So 3x plus 5x, 8x. I'm going to put the numbers together. 15 plus 1, 16. Divide both sides by 8. So the answer is 2 is bigger than x, or you can also write this as x is less than equal to 2. Both of these, they mean the same thing, okay? And that's it for this. What about this one? How do we solve a quadratic? You have to man it. You have to factor it, man it. To factor it, you have to man it. So we're looking for two numbers. When they multiply, you get -4. When you add them up, you get +3. So what are the two numbers? So it's +4 and -1. So x plus 4, x minus 1 greater than 0. We know this means that there's a intercept at -4 and at +1. This is opening up. And we need the function to be positive, right? Strictly positive. Greater than 0 means strictly positive. So where is this function strictly positive? In other words, where is it above the x-axis? So it's when x is less than -4 and when x is bigger than 1, right? That's when it's above the x-axis, and that's the answer. Interval notation for this is going to be annoying. It's this. -∞ to -4. So any number from -∞ to -4, which is talking about this side, it's going to be above the x-axis. Union, when you have multiple ranges, we use union, and then 1 to +∞. There we go. Both of these solutions, they mean the same thing. One at the bottom one is the interval notation. The top one is the set notation. Sketch the graph. So we don't have to solve anything. We just have to sketch them. This +1, does it move it to the right or to the left? So x lies. Okay, so +1, you'd expect it to go to the right, but it's actually going to the left. So we're not going to be super precise here. This is x squared. So the transformation here is that it moves 1 unit to the left So the vertex now would be at -1, 0. It's moved 1 unit left. And what about the -3? Does it move it up or down? This -3. Minus means y is as you see it. It's going to be down. It's only the x that lies. Y is as you see it. So this one's going to be going down, okay? So the final sketch for this, you just take this point, move it down here. So that point is -1, -3, and then it'll look like this. There we go. And that's the final answer. Sketching C isn't as easy. And this is going to be the goal of this chapter, is like, how do you sketch something like this? What's the name of this function? What would you call this? It's a rational function, rational. So to graph this, you need to first do your asymptotes. You want to find your vertical asymptotes. That is when denominator is 0. For which value of x is the denominator 0? -2. So we have a vertical asymptote at x equals -2. Then you want to find the horizontal asymptote. And the way this works is that if the degree of the denominator is bigger than the degree of the numerator, then you'll have a horizontal asymptote on the x-axis, y equals 0. If the degree of the denominator is equals to the degree of the numerator, then your asymptote will be the leading coefficient of numerator divided by the leading coefficient of the denominator. So is the degree in the numerator bigger or equal to the degree in the denominator in this case? It's equal. What's the leading coefficient in the numerator? 2. In the denominator, it's 1. So you have it at 2. So that's the first step. Second step, you're going to find your x-intercept by setting y equal to 0, or f of x, this is y. Setting that equal to 0 and solving for x. How do you solve this for x? So get rid of the denominator. Step number 1, get rid of the denominator. So you multiply both sides by that denominator, okay? So here, it'll be 0 equals 2x minus 4. 4 equals 2x. X equals 2. So that's your x-intercept. And then we want to find our y-intercept by setting x equals 0. X-intercept is when y is 0. Y-intercept is when x is 0. So 2 times 0 minus 4 is minus 4. 0 plus 2 is 2. So we have -2. So now let's see what we have. I'm going to make a rough sketch here. So our vertical asymptote is at -2. So right here. That is going to be our vertical asymptote at -2. Our horizontal asymptote is at 2. So 1, 2. This 2 is our horizontal asymptote. And then our x-intercept is 2. So right here is our x-intercept. Our y-intercept is -2. Right here. So these functions, okay, rational functions usually always look something like this. They're gonna be like mirror images across some asymptotes. And they cannot ever cross the asymptote. So you can always verify this by plugging in points. But here's a shortcut. Because we have a point here, we have a point here, and we know we cannot cross these asymptotes, right? There is no way that the curve comes in like this or something like that. No, that's not going to be possible, because if that were the case, then it would cross the asymptote. The shape has to make sense. The only way these 2 points would make sense, and referencing the asymptote, is if our line comes from here like this. It writes the asymptote, goes into the point, and it continues to write the asymptote. So I didn't do a very good job of sketching this, but maybe if I go down here, I can fix this. So it'll look like this. It's going to come through the asymptote. It's going to go through the 2 things, and it's going to write the asymptote again like that. Rational function always has n+1 components, where n is the number of vertical asymptotes. So if you have 1 vertical asymptote, there's 2 pieces. If you have 2 vertical asymptotes, there's 3 pieces. So here we've done 1 piece, there's going to be another piece. And usually it's always going to be mirrored across, not to the side, but across. You can always verify this. I'm going to plug a value of -3, and I'm expecting a value above 2. If I get a value above 2, I know I'm here. If I get a value of less than 2, I know I'm here. Okay? So let me just plug 3 in there. So 2 times 3 minus 4 over 3 plus 2, 6 minus 4 over 5, 2 over 5, it's 0.4. Sorry, I messed this one up big time. It's -3 I meant to plug in, not 3. Because I want to see what happens to the left of this asymptote. So I should have plugged -3 in there. Let me try that again. 2 times -3 minus 4 over -3 plus 2. -6 minus 4 over -1. That is -10 over -1. That's +10. So at 3, I'm at +10. So +10 would be somewhere up here, right? And the only way it's going to make sense now with respect to the asymptotes is if it comes this way and if it goes like this. And there you go, that's the sketch. Cool?
Yeah.
This shape, okay, this shape is called concave up. Concave up. This thing here is called concave down. Some terminologies there. If it's opening up, it's not technically opening up, but it's like this. This is called concave up. This is called concave down. Not even gonna bother with the quadratic. For D, it's also very simple. This -2, does it go to left, right, up, down? Goes to the right. So root x looks like this. The parent function root x looks like this. Goes through 0, 0, 1, 1, 4, 2, 9, 3. -2 means this thing is just going to shift 2 units to the right like that, and you're done. That's it. All the x values just shift 2 units to the right. Y values are exactly the same. Evaluate each limit. So x squared minus 4, here's where graphing is would be very helpful. So x squared minus 4 goes through, this is simple, right? Not gonna waste too much time. Goes through plus minus 2. That's our gonna be x-intercepts. And for the y-intercept, it's gonna be -4, which is also the vertex. So this function looks like this. the question is, as we go to the x value of 2 minus means approaching the x value of 2 from the left, approaching x equals 2 from the left, okay? So what I mean by that is, what's the y value right here? Right there. What's the y value? Well, the y value is 0. At 2, it's exactly 0. At 2 coming from the left, it's also exactly 0. X equals 2 plus would also be 0. That just means we're coming at it like right here. What's the y value, right? What's the y value just above 2? Maybe like 2.001. What's the y value? And it's gonna be exact. It's not gonna be exactly 0, but the limit will be exactly 0. It's approaching 0, right? Because this graph is going this way. So at this point, the y value is gonna be approaching 0. Same thing from both directions. It's very simple when you're talking about what is this? A quadratic, a polynomial. Limits are super simple. It gets a little bit more difficult when you're talking about a rational function as this one right here. So this is a rational function, not that easy to graph. Well, the goal is to find the limit. Okay, should we graph this? Let me think. No, we shouldn't. When you're doing limits, actually when you're doing anything, always factor, simplify if possible. If you simplify, things become much easier for them. For us, I guess. Who's them? For us. So I'm gonna try and factor this. Again, not gonna waste too much time. If you're not sure about how to factor a quadratic, watch our previous videos. I'm just gonna man this in my head. It'll be +5 and -2. So like that. Can we cancel out the x minus 2's? Yep. So this cancels out with this. So the answer that we get, now there was an issue here. The issue was we couldn't straight up plug and chug. For limits, the first thing you do, which only works like 1% of the time, is you straight up plug that number, put it into the function. If we were to do this, you'll see that we will get a 0 in the denominator, yeah? So that's not good. You can't have a 0 in the denominator. So our goal here was to, well, let's cancel the denominator if possible. And we did cancel it. Now, after we've canceled it, let's plug the x value in the function. So this becomes 2 plus 5, right? 7. Final answer. So the limit for this function is going to be 7 as our x approaches 2. For this one, can we plug 3 in there as is? Like right now as we see it, can we plug 3 in there? No, because you'll get a 0 in the denominator. So what's our approach here? We have to factor this. To factor this, we need to use a difference of cubes in the numerator. We've heard about difference of squares. We've also done difference of cubes. Here's the formula for difference of cubes. A cubed minus b cubed is equals to a minus b times a squared plus ab plus b squared. If you don't know this, you won't be able to solve this. So we're looking at x cubed minus 3 cubed. 27 is 3 cubed. It has to be in this form, b cubed form. So a is x and b is 3. So this becomes x minus 3. A minus b is x minus 3. X squared, so that's x squared, plus ab, so that's 3x, plus b squared, that's 9. Like that. Okay? So limit as x approaches 3. X minus 3 in the denominator, haven't touched this, but the numerator now becomes x minus 3, x squared plus 3x plus 9. Now we can cancel out the x's. Once you cancel out the x minus 3, that was the issue, that we couldn't plug it in because that would give us a 0 in the denominator. Now we plug the 3 in for the final answer. So it'll be 3 squared, because this is the only thing that's remaining, 3 squared plus 3 times 3 plus 9. So it's 9 plus 27 plus 9, 45. Final answer, done. It says determine the derivative of each function. Just the first derivative. What's the first derivative of this? So you bring the 2 down, okay? You have to bring the 2 down. Everything inside the bracket stays as it is. Take 1 away from the exponent, and then the chain rule. You multiply this by the derivative of the bracket. What's the derivative of the bracket? 6x minus 6. There we go, and we're done. Easy peasy. For this one, you have to use quotient rule. Not gonna bother with that. Let's look at this one. This one looks a little bit complicated. So again, we have a numerator denominator. I don't know what will be easier. Let me think. Let me show you both ways, actually. We use the product rule approach, and we're gonna use the quotient rule approach. If you're using the product rule approach, both things have to be on the same level. You can't have a denominator. So I'm moving this. So this becomes 2t times t minus 4. Remember, it was a root. Okay, it was a root, and I'm moving this root upstairs. What is the exponent of this root right now? Negative 1 over 2, like that. So what does product rule say? Product rule says f prime g plus f g prime. So here it would be, so the derivative would be f prime, so that's 2, because this is f and this is g. So it'll be 2 times the second function as it is, plus the first function as it is. What's the derivative of this? What is the derivative of this? Negative 1 over 2. Negative 3 over 2. You don't have to factor it, but because I want to show you that they both give you the same answer, I'm going to factor this. 2 over the root of t minus 4 plus 2t. Actually, these two cancels out. And then minus 1, I guess this becomes minus. So there's still a t in the numerator. And in the denominator, we have t minus 4 to the power of 3 over 2, which means it's like this. T minus 4 to the power of 3 over 2 is t minus 4 to the power of 2 over 2 times t minus 4 to the power of 1 over 2. When you multiply, you add the exponents, and 2 over 2 is a 1. You get this. From here, we need to take the LCD. So you need to multiply this by t minus 4. You need to multiply this by t minus 4. So the answer is 2t minus 4, minus 8, sorry, minus t, all over t minus 4 times root t minus 4. So it'll be t minus 8 over t minus 4 to the power of 3 over 2, something like that. That's as far as you can simplify this. So that is using the product rule approach. What you can do is you can also use the quotient rule approach, where you can say, well, this is f and this is g, and quotient rule says f prime g minus fg prime all over g squared. So here f prime is 2, g is, well, root of t minus 4, minus f is 2t, and the derivative of this is going to be 1 over 2 t minus 4 to the negative 1 over 2. Because this is it right now, the derivative, 1 over 2 comes front, bracket stays the same, and you take 1 away from that 1 over 2. All over g squared. So if you square this, what happens to the root? Disappears, goes to Narnia, see you later. All right, now what? This and this cancels out. So we have 2 root t minus 4 minus t over root t minus 4, all over t minus 4. Just going to focus here. The common denominator is t minus 4 root. So you have to multiply this by t minus 4 on the numerator, which is the same thing as squaring it, and t minus 4 on the denominator. This and this cancels out. You'll get t 2t minus 8 minus t all over root t minus 4. Now here's the important thing. Does this go to the second level or does it go to the top level? So we have a over b all over c. That's the case right now. That is the same thing as saying a over b divided by 1 over c. Whenever you have a division, or sorry, just divided by c, whenever you have a division, you need to flip it upside down like this. So you get a over bc, okay? Which means, where does it go then? Does it go to the top level or the second level? Second level, so it comes right here. Times t minus 4. And this is the same thing we have here. 2t minus t is t minus 8. And you have a power 1, you have a power 1 over 2. 1 plus 1 over 2 is 3 over 2. Okay? Boom. Done. So the same answer. So you can use either approach, whichever one you think is easier for you. They will both give you the same answer. Let's quickly talk about end behaviors. So end behaviors is what happens at the end of the functions. So for A, it's a quadratic opens up, right? Like that. So when x is positive infinity, what's the y value? So again, this is all about infinity. So there's negative infinity up here, positive infinity up here. There's negative infinity up here for the x, right? And then for the y, it's the same thing. So when x is positive infinity, the y value is positive infinity as well. Yeah? What about when x is negative infinity? What's the y value? It's positive. So we can say when x goes to positive or negative infinity for A, y all goes to positive infinity in both cases. And that's it. Cool? So that was because it was a quadratic, it was opening up. Let's do B. It's a cubic. Which quadrant does it start in? It's a negative cubic. Which quadrant does it start in? Where does it end? Yep. So it starts here, it ends here, right? So when x is going to when x is going to positive infinity, where's y going? Positive infinity as well. When x is going to negative infinity, where's y going? So when x was going to positive infinity, y is going to negative infinity. Because there's negative infinity down here, positive infinity up here. And when x is going to negative infinity, y would be going to positive infinity, right? That's the answer. So it's alternating. If the degree is odd, the n behaviors are going to be alternating like this. It'll go in different places. Whereas the previous one, y was going to the same position from either direction. That is called an even degree. If your degree is even, the n behaviors, the y values, what they do, they are the same from both sides. But here this is an odd degree, then the n behaviors for y's will be different, okay? Okay, we're just gonna quickly speed run these two. C is a negative cubic, starts here, ends here. Will look something like this, not cubic, quartic. So as x goes to positive infinity, y, so the x goes to positive infinity, y is going to negative infinity. Same thing on the other side. As x goes to negative infinity, y is still going to negative infinity. And that makes sense because even degree function, the n behaviors are the same. Y cannot be alternating. Both y's have to go to the same location. Finally, for D, it's a quintic function. Now it's a positive degree 5 function. It's the same thing as degree 4. Starts here, ends degree 3, sorry. Starts here, ends there, or looks something like this. So over here, as x goes to negative infinity, y goes to negative infinity. Over here, as x goes to positive infinity, y also goes to positive infinity. Cool? That's it. State the equation of the horizontal asymptote of each function. Again, I'll give you the guideline, and you have to maybe memorize this for horizontal asymptotes. Degree in the numerator, if it's equal to degree in the denominator, then you take the leading coefficient of the numerator over leading coefficient of the denominator. If the degree in the numerator, I just make numerator, if it's less than the degree in the denominator, then it'll be on the y-axis, on the x-axis at y equals 0. So for A, degree in the numerator is less than the degree in the denominator. Here, there's an invisible x0. There's x1, numerator is less, y equals 0. What about B? Where's the asymptote? Notice the degrees are the same. You have x power 1, right? So the horizontal asymptote, the leading coefficient of the numerator is a 4. The leading coefficient in the denominator is a 1. Not because of this one, it's because of this one. The numbers that's attached to the 1. So it's going to be at y equals 4. What about C? It's 1 over 2. 3 over 6, 1 over 2, okay? 3 over 6, 1 over 2. The last one, 10 over 5. So let me just show you. Because the coefficients, the degree is the same, for C it's going to be 3 over 6, which is 1 over 2. Here, X's coefficient, again, the degrees are the same thing as C. It'll be 10 over 5 at 2. and done. Easy peasy. I'm not gonna use a graphing calculator here. All right, let's talk about this. We're gonna see where a function is increasing or a function is decreasing and where it's 0. It's only horizontal, and here's a key part. It's only horizontal at turning points, okay? At strictly turning points. It has to be smooth. By this, I mean it has to be smooth. So let's go one by one. This question, very simple. A, it's increasing up until this point. From negative infinity to negative 1, it's increasing. From negative 1 to 2, it's decreasing. What's happening after 2? It's increasing again. So you can say from 2 to positive infinity, it's increasing. And the turning points are right here and right here, 2 and negative 1. And that's it. We always say it in terms of the x values. B, again, this is like just like pattern finding. That's super simple. It's decreasing here. It's increasing here up until here, yeah? And then it decreases again here. And there are 2 turning points. That's where the slope or the tangent line will be 0. For C, let's go one by one. Is this one on the left, is it increasing or decreasing? Is it going up or down? So this one is increasing. What about in the middle? Decreasing. What about at the end? It's also decreasing. There are no turning points. So there are no points where the function, the tangent line is horizontal. Needs something like this. Okay, D is again very simple. It's decreasing here, it's increasing here. It's decreasing here, it's increasing here. Now this part is very important. It has to be a turning point, okay? It has to be a turning point, and that turning point has to be relatively smooth. These are called cusps. Looks like this. Like a bird. Those do not count as turning points. It has to be smooth. They have to leave some room here at the end for it to like nicely turn and go over, okay? The issue with cusps is that only one point is turning. It does have a vertex, just like this does. At that point, you have a point. Here, you also have a point. I guess what I'm trying to say is that the transition from this point to this curve is smooth. Whereas for a cusp, the transition is pointy. This do not count as turning points. Cusps are not where the tangent line is horizontal, where the slope will be 0. The slope here and here won't be 0, okay? Only at turning points of a curve, it'll be 0, not at these pointy ends. All right, let's move on from here. Local maxima, local minimum, we've already kind of done it. Let's talk about critical numbers. Critical numbers, we've already done this. It's when the first derivative, you set it equal to 0 and solve for x. These represent turning points. Critical points are the turning points. Why is it called a critical point? Because in a critical point, look at what happens to the function. Is it increasing or decreasing here? It's increasing, and then it hits that turning point and it starts decreasing. That's a critical point. The other way also works. So at critical points, the function changes its path, basically, or the pattern. It is increasing and then it's going to decrease, or vice versa. That's a critical point. It's always going to happen at turning points. To find the turning points, take the first derivative and set it equal to 0. Cool? So here, it's very simple, isn't it? What's the first derivative? 4x cubed minus 24x squared, 36x. Set this to 0. We have a cubic. Always pull something out. Whenever trying to solve an equation, always pull something out if you can. Here, what can we pull out? What's the GCF? For x. We're left with x squared minus 6x plus, it's not 12, 9. Like that, yeah? So this is going to be either 4x is 0 or x squared minus 6x plus 9 is 0. This means that x is 0. This, again, you know how to man this. This is going to be x minus 3 whole squared is 0. So that means x is 3. And notice how this one was a order 2 polynomial, right? Order 2 x-intercept. Let me call it order 2 x-intercept. So for this function, these are the critical points. So now how do we know which one is maximum, which one is minimum? Well, you plug it in. You straight up plug it in. If you get a higher number, that's gonna be the maximum. If you get lower number, that's gonna be the minimum. It's easy as that. So here, let's find f of 0. I'm gonna plug 0 in here. I'm gonna get a 0. Then I'm gonna plug f of 3. I'm gonna do this on a calculator. So 3 power 4 minus 8 times 3 cubed plus 18 times 4, sorry, not 4, times 3 squared. I get a positive 27. So what does this mean for us? Is 0, 0 a minimum or a maximum? It's a minimum, right? What about 3, 27? Is that a minimum or a maximum? Maximum, exactly. So let's just quickly graph this to verify our results. So x to the power of 4 minus 8x3 plus 18x squared. So this is what it looks like. So at 0, 0, it's definitely a minimum. Yeah? What was our other point? 3, 27. All right, here we go. Is there a range given? Nope, there's no range given. That's why sometimes it's important to graph the function. Look at this point. Is this a maximum? Does it look like a turning point right here? And a turning point, it has to go in the same direction. If it was a turning point, then it should have gone down like this. It needs to go back to where it came from, okay? That's a turning point. Is that a turning point there in the middle?
No.
No, so that is actually not our maximum. I'm sure they cheated here. Let's see. Actually, they didn't. They did cheat. They always graph it out. So the conclusion is that x equals 0 is definitely a minimum, okay? But x equals 3 is neither. It's neither a maximum nor a minimum. I'll tell you what this is, and we can talk more about this tomorrow. Notice what happens to this function at this point. This is concave up or concave down? It looks like this. It's a concave down. So that's before that point, we have a concave down. After that point, what do we have? Concave up. So now, critical value, right? Critical value, you go from increasing to decreasing or vice versa. Nothing to do with concave. I can't say that word, but the word is concavity. That's the word. Nothing to do with this critical value. That is the first derivative. Set this to 0. So it's talking about increasing, decreasing. That's what it's useful for. Now, there's another term. This is called a point of inflection. That's the word, point of inflection. Now that happens when you set the second derivative equal to 0 and solve for x. What's the important thing about point of inflection is that it goes from a concave up to a concave down or vice versa. Okay? See over here, both of these, there's a point where it alternates from being concave down to the other one. That is called a point of inflection. And to find a point of inflection, we will set the second derivative equal to 0. That's the idea. Cool? All right, let's call it there for today.
Okay, thank you.
See ya.